Welcome to lecture number 2, which is about algorithms to solve shortest path problems. I'm going to start with some basic definitions and basic observations about shortest path problems. And then during the rest of the lecture, we are going to look at 3 different algorithms for different versions of shortest path problems. So I think that the shortest path problem needs no motivation. Many of us use it all the times when, for example, driving from A to B and using a navigation system. But as a matter of fact, the shortest path problem is not only interesting as it has an immediate application, it also pops up as a sub-problem in many, many different combinatorial optimization problems. So in order to solve those more complicated optimization problems, along the way, we have to solve a couple of shortest path problems. And therefore, it's important to have fast algorithms for that. So what is the definition of the problem? We are now, in contrast to the previous lecture, are having a directed graph. So the edges of the graph also have a direction. As usual, n is going to be the number of vertices of the graph, and m is going to be the number of edges of the graph. The edges have edge lengths or costs, and there is 2 designated vertices, s and t, and we want to compute actually the shortest path from S to T, okay? And here's a little example down here. So this is an example graph. You see S and T here, and as a matter of fact, the shortest path from S to T in this example is, if I'm not mistaken, this path here, which has a length of 2 plus 3 plus 4 makes 9. As it turns out, when we want to compute the shortest path from S to T, in fact, we have to compute the shortest paths from S to all the other nodes in the graph. Why is that? Well, because in principle, you can think of it in this way. Any node could be an intermediate node on a shortest path from S to T. So in fact, what we are going to compute is a so-called complete shortest path tree, which includes all the shortest paths from S to all the other nodes in the graph. And that is actually this tree here in this figure, right? The problem is defined for directed graphs, so edges have a direction. If we happen to have undirected graphs, we can just model that by replacing one undirected edge here of length 2 with 2 directed edges in opposite directions with the same length 2. So it's no loss of generality to only look at the problem for directed graphs. So let's continue with some basic remarks. So by C of P, we denote the length of a path. And what is the definition of a length of a path? Well, that is just the sum of the edge lengths or edge costs of all the edges in that path, right? Like in this little example down here, the sum of the edge lengths of all the involved edges, that's the cost or the length of a path. Also note that it might be possible that some of the nodes of the graph are not reachable on a directed path. So there's a little example down here. Oops, excuse me. Where this vertex V is not reachable because there is simply no path from S to this vertex V. Next observation is that there might exist a negative length cycle in a graph, in which case the shortest path to the vertices on that negative length cycle is not well defined. So there is an example down here where we have a cycle of length -1 plus -1 plus 1, which is -1. And by walking along the cycle again and again, I would decrease the distance to reach the corresponding vertices. So a shortest path, for example, from S to U or from S to V is not well defined. Now, if neither of these 2 things happens, so if all the vertices are reachable and there exists no negative length cycle, then actually there exists a simple path. So that would be a path which does not make any circuits or cycles. There exists a simple path from S to all the other vertices of the graph V. And if there exists a path, there also exists a shortest path. We're making the following definition with respect to shortest paths. So we define the distance function delta, which is defined for all the vertices of the graph and is going to represent the shortest path distances to reach a vertex V from the start vertex S. Okay, so delta of V is just taking as the infimum of all paths which exist to reach vertex V. Okay, so if there exists no path at all to reach vertex V from S, that distance is to be defined plus infinity. And if, for instance, there exist infinitely many paths because there would exist a negative length cycle along which we could walk as often as we want, this infimum would evaluate to minus infinity. And that is also correct because then the distance to reach vertex V from the start vertex S would be minus infinity. And otherwise, it would be a finite value, which represents the shortest path length to reach vertex V. And here's the first little claim that I would like to show you. So delta represents shortest path distances, and shortest path distances always have to fulfill the so-called triangle inequality. So that means the distance to reach vertex V is never more than the distance to reach another vertex U plus the length of the corresponding arc if it exists from U to V. Okay, you could think of it like this. We have U and we have V, and there might be a path to reach vertex U. There is an edge from U to V which has a certain cost, and then the shortest path from S to V, this one here, cannot be longer than this specific path here because it's the shortest path. And we call edges tight when they actually lie on a shortest path. So a little example here for tightness. There is a graph here with 3 vertices. The distance to reach vertex U, well, that's not too difficult here, would be delta of U would be 1 here. The distance to reach vertex V would be along this path here. So correspondingly, delta of V would be 2. And then there is yet another path. There is a path from S to V here of length 3, but this is not the shortest path, and hence this edge here is not tight, while the other ones, which are colored in red, are actually tight edges. Now let's look at the proof for this little claim here. So here again is the triangle inequality that we want to prove for shortest path distances for each existing arc in the graph. Okay. Certainly, if on the right-hand side, delta of U, the distance to reach U, is plus infinity, there is nothing to prove, so we can forget about that case. And otherwise, there at least exists some path in the graph from S to U, and hence the following is true for all SU paths P. We have that the shortest path distance, so delta of V, so the shortest path length to reach vertex V, cannot be more than the length of such a given path. So that would be C of P, which is a path from S to U, right? Plus the corresponding length of the arc from U to V. So if you look at the figure, this is true because there exists some path P from S to U, and then it must be the case that the shortest path length, which is denoted delta of V, so that would be this path here, right? That cannot be longer than the length of this specific path here, right? Now, and if this inequality is true for all SU paths, we can also take the infimum over the right-hand side here. So we can conclude that delta of V is at most the infimum of all these lengths for all SU paths, and that is actually equal to delta of U plus the cost or length from U to V. And that's it. Let us collect some more basic observations. And another basic observation is that subpaths of shortest paths are actually shortest paths again, right? So if I have a shortest path here from V1 to VK, then the corresponding subpath from any two vertices I and J in between, so this subpath is also a shortest path from VI to VJ, and that must be true obviously, because otherwise, if there would be a shortcut from VI to VJ, then the original path was not the shortest path. Another observation is concerned with the algorithms that we are going to look at, because in some sense, what we're going to compute is only distances to vertices in the graph and not the paths themselves. And I would like to motivate why we can do that. So what interests us, and that is summarized here in fact number 2, what interests us is the vertices which actually have well-defined shortest path length. So we could define a subgraph G prime by taking only those vertices where the shortest path distances are actually well-defined, so neither minus nor plus infinity, and all the edges between these vertices. And we are selecting all the edges that are tight, actually, once we have computed these values delta, okay? So there is a little example here. So there's a little graph down here, and when you look at it, you will see that there is a negative cycle here, okay, of length -1. So in some sense, we are not interested in these 3 vertices here on a negative length cycle. And there also exists a vertex here which is not even reachable from the start vertex S. So the start vertex S is actually here, right? And this vertex here is not reachable. So also in some sense, we are not really interested in that vertex here. And we are only interested in the rest of the graph. And then for this small example, G prime would contain S and the corresponding vertex, 2 other vertices here, this one and this one, right? 2, 3, and 1. So this would be G prime, our object of interest. Notice that I have drawn all the edges here, which is also true because all these edges here are actually tight. So delta of S, the distance from S to S is 0, obviously. The distance from S to this vertex down here, so delta would be 2 here, and the delta would be 3 here. So all the edges are actually tight, and therefore they are all contained in the subgraph with all the tight edges. And as a matter of fact, this subgraph G prime now contains all the shortest paths by definition, and because it contains all the tight edges. And in order to, once we have computed these delta values, the shortest path lengths, we can compute the subgraph G prime. And once we have done that, we could, for instance, compute a spanning tree in this graph, which would be, for instance, this one, and thus obtain a shortest path tree. So given the shortest path lengths, we can very easily reconstruct also the shortest paths themselves. So in the following, we are just going to focus on computing these values delta in any given graph, because we know that the rest, the lengths, the paths themselves can be computed very easily. Okay, so this is again summarized here on the next slide. And hence it is totally okay to focus on just the computation of the distance values. Now we are going to look at three algorithms. That's what I said, and that is essentially three main cases which are different and interesting. So with respect to computation time, notice that n, as usual, denotes the number of vertices, and m denotes the number of edges of a graph. So for arbitrary directed graphs, we use a so-called label correcting algorithm, which includes detection of negative length cycles, and that will have a computation time of order m times n. And since the number of edges of the graph cannot be more than order n squared, this is essentially a cubic computation time, okay, in the worst case. So this is for arbitrary directed graphs with no restriction on the lengths of the arcs. If we have directed graphs with only non-negative arc lengths, that's a special case, we can actually do better, and that is Dijkstra's famous algorithm for computing shortest paths with non-negative arc lengths. We get a computation time of the order n squared, so we shave off one factor n from the computation time by exploiting the knowledge that the arc lengths are non-negative. Even faster, shortest paths can be computed even quicker in acyclic directed graphs. So that would be graphs which do not contain any directed cycle. And such graphs can essentially be ordered along the line such that all the edges go from left to right, for instance. And once you have this interpretation, or once you have sorted the vertices of the graph in that order, you can set up a very simple dynamic programming algorithm, and you even get a linear computation time, right? Because notice that the encoding length of a graph is certainly the number of vertices and the number of edges of the graph. So better than this is hardly possible when you want to compute shortest paths, and you at least have to look at the whole graph. So we are not going to do that in the lecture. Instead, we are going to look at another algorithm at the end. So for the time being, we will focus on arbitrary directed graphs, which may also include negative arc lengths, and directed graphs with non-negative arc lengths. I start looking at these algorithms, or the basic building brick of these algorithms, by the following observation. So we are going to work with node labels D in the course of all these algorithms. So in the beginning, these values D are not yet shortest path lengths, but at the end, they will represent the true shortest path lengths. And this lemma is quite powerful and quite important. So if we have such labels D, and we happen to know that these labels D are upper bounds on the true shortest path lengths. Okay, so you could think of D being plus infinity, then this is certainly fulfilled. Then the following is true. These labels D are actually equal to the true shortest path lengths if and only if, so that's a characterization, for all the edges, the triangle inequality is fulfilled. Okay, so if these distance labels D fulfill the triangle inequality for all the edges in the graph, and they are upper bounds on true shortest path lengths, then they already must be equal to the shortest path length. Let's look at the proof. So it's immediate that this is a necessary condition. So for instance, assume that we have node or vertex labels which do not fulfill the triangle inequalities. So there exists a pair of vertices u and v where the triangle inequality is violated. Okay, then we know that d of u is an upper bound on the true shortest path length. So this is larger or equal than delta of u, right? So therefore, I get this inequality here. And next, by the triangle inequality for the shortest path length delta, I know that this is a lower bound for delta of v, right? So this is just a triangle inequality for the true shortest path lengths. So hence, we get that d of v is strictly larger and delta of V. And then these labels D do not represent shortest path lengths. So it's a necessary condition that the triangle inequalities are fulfilled if these distance labels D want to be true shortest path lengths. But it's also a sufficient condition, and to that end, we look at any given vertex V in the graph and recall that these distance labels D are supposed to be upper bounds on the true shortest path lengths. And for the time being, let's assume that the distance to V is not minus infinity, so it's well defined. Okay. Now, that means that we can pick a shortest path from S to V. Such a shortest path is well defined, and this is just one of these shortest paths if there is more than one. And let's say length of P denotes the length of this path. Okay. By the choice of P, this is equal to the true distance. Okay, so, all right. And now we just use the triangle inequality backwards along this path. Okay, in the following way. We assume, that's our assumption, the distance labels D fulfill the triangle inequality. So we can use the triangle inequality on the edge from U to V, right? So we know that the distance, or d of V, is at most d of U plus the length of the corresponding arc from U to V. And now we look at the predecessor of U. So there is some predecessor of U, which we called W, and we can again use the triangle inequality along this arc. Okay, this gives us the next inequality. So d of U is smaller or equal than d of W plus the length of the arc from W to U, and so on and so on. So I get that d of V is at most, when I'm just finishing with the starting vertex S, is at most d of S plus the sum of the edge lengths of all the edges on the path, and that is just the length of the path. Now d of S is equal to 0, right? The distance from S to S is 0. So this is just the length of the path. But this path was chosen to be a shortest path from S to V, so that is equal to the true distance from S to V. And hence we get two inequalities. D of V is larger or equal than delta of V, and D of V is smaller or equal than delta of V. Therefore, they must be equal. Now what if, that is what I just skipped, what if delta of V is minus infinity? Well, actually also then the same proof or the same argument is true, with the only exception that this shortest path or a finite shortest path doesn't exist. But we could do that for any path which is maybe, or which is then walking along negative length cycles. So essentially what we would get is that the length of P can be made arbitrarily small. Think of this as minus infinity. And then we also get that d of V is equal to minus infinity, and that is also the true value, the correct value. Okay. So this already brings us to the basic and fundamental algorithmic idea, which is underlying all these algorithms to compute shortest paths in graphs. So we start with any vector of distance labels D, which are upper bounds on the true shortest path lengths. And you should really think of this as d of V being plus infinity, for example. And then what we need to do in order to get the true shortest path lengths is we have to correct all the violated triangle inequalities until no violated triangle inequality exists. So we know by the previous lemma that when all the triangle inequalities are fulfilled, then we have computed the true shortest path lengths, as long as we are also making sure that this invariant is maintained. So that is the building block of all the algorithms that we are going to look at. That is correction of the violated triangle inequalities. And in many textbooks, this is called relaxing an edge UV. So relaxing an edge UV just means we are checking if the triangle inequality is actually violated. Okay, so if a triangle inequality is violated, I'm actually making an update step and I'm correcting the triangle inequality. So I'm setting d of v equal to this value here, with the idea that this value here represents the length of some path to reach the end vertex v, and hence the true shortest path length to reach vertex v cannot be more than that. It could be equal to this, but there could also be later on, or there could also be another yet shorter path, and then it can be further reduced. But if it's still larger than this value, it has to be corrected. So with this label correcting idea, or with this relax function, we can already build our first algorithm to compute shortest paths in arbitrary graphs. And that is the so-called Bellman and Ford algorithm. It's as simple as it could be. It works in n-1 so-called phases. And what do we do in each of these phases? We go over all the edges of the graph in an arbitrary but fixed order, say by their numbering. And we are considering the edges in this order and checking if we have to update the triangle inequality. And if we have to update or can update it, we do. Okay, so we are relaxing all the edges of the graph. And then we are doing the same. We are relaxing all the edges of the graph. And then we are doing the same again. And we do that n-1 times. So this is the description of the algorithm. We start out with distance label 0 for the start vertex, plus infinity for all the other vertices. And then, as I said, n-1 times we do the same. We go over all the edges of the graph and relax the edge. Okay. So if necessary, we update the triangle inequality. Here's the theorem. After termination, the distance labels will be correct, representing the true shortest path length for all the vertices for which this is well defined. Okay. Now let's see why this is true. The first observation is the uninteresting part of the graph. So this concerns subgraphs with vertices which are not even reachable. Such subgraphs have no ingoing edge looking from S, and therefore the distance labels will remain at plus infinity, and that is also the correct value. Okay, so from here on, we may as well assume that all the vertices are actually reachable from the start vertex S. Now, let's consider a vertex for which the shortest path length is well defined. Okay, so that means the true distance from S is somewhere between minus and plus infinity. So we know that there exists a shortest path to that vertex V. So let's pick one. So this is this path P here, and it consists of vertices V1 up to Vk minus 1, where Vk is the last vertex V itself. Okay. All right. The most important thing that we need now is the insight, the fact that I mentioned earlier, namely that subpaths of shortest paths are again shortest paths. So what does that mean? Well, look at this figure here. This is the shortest path that we have picked. Okay, it's the shortest path from S to V. But we also know by this fact, this observation, that this is also a shortest path to V1, and this is also a shortest path to V2, and so on. So therefore, after the first phase of our algorithm, we have scanned all the edges of the graph once. So in particular, this one here. Before the first phase, the distance label of the starting vertex was equal to 0, which is the correct value. And we did do relax SV1, so we did relax this edge, so update the corresponding triangle inequality if that was necessary. And that means after this phase 1, d of V1 will be equal to d of S plus the corresponding length of the edge, SV1, right? And this is the correct value. This is equal to 0. Okay, so after the first phase, the distance label d of V1 for this vertex here, for the first vertex here, is correct. But this argument goes on inductively. So after the second phase of the algorithm, what do I know? Well, before the second phase, I already know that these two distance labels have been correct. So in particular, the one of the second vertex on this shortest path. Again, I was scanning all the edges of the graph in the second phase, in particular also this one. So therefore, I'm sure that the corresponding update has been made, and after the second phase, the true distance of V2 has been set. So d of V2 is equal to delta of V2. Okay, so this just goes on inductively along this path. So after k phases, we know that the kth vertex on this shortest path has the true label, so the true shortest path distance label, and that was our vertex V. So it was arbitrarily chosen. Now, how long could k possibly be? Well, k is the length of a shortest path, and how long can the shortest path in a graph be? It cannot be longer than n minus 1 when n is the number of vertices of the graph, right? Therefore, n minus 1 phases are certainly sufficient for each of the vertices V. Okay, so that finishes the correctness proof for all the vertices where the shortest path length is actually well defined. Okay, so we are almost done, but there is a little bit more that we can observe, namely what happens when there is negative length cycles in the graph. Well, if there is negative length cycles, it will actually be the case that the triangle inequality is still violated after these n minus 1 phases. Okay, so we have the situation as follows. There will be a violated triangle inequality, and the claim that I make is as follows. If some triangle inequality is still violated after n minus 1 phases, then indeed we will have a negative length cycle, and we can also compute that negative length cycle. So let us see how this works. So here is our violated triangle inequality, which we assume still to be violated after we have done n minus 1 phases of the algorithm. First observation is that the distance label of vertex u, because of this violated triangle inequality, cannot be infinity. So it's actually finite. Okay. And as a matter of fact, that means that there exists some path from S, from the start vertex S to that vertex u. And I claim that for all vertices with a finite distance label, I can construct a unique path, which I call PU, of predecessors in the following way. Well, we look at U, and of course, it has a finite distance label, so some other vertex, some predecessor, was responsible for that finite distance label. Okay, so vertex U is here. We have done an update of its distance label along a certain arc, and that gives us a predecessor. And also that predecessor has a finite distance label, and that because there was an update along an arc, and that gives us another predecessor. So we start with U, it has a predecessor, that predecessor has a predecessor, etc. Now what could happen when we follow this construction? Well, one thing that could happen is, for instance, that we follow this list of predecessors, but we end up in a cycle. So that means in our path construction, we follow backwards along this path, and we end up iterating in this cycle here. I claim that in that case, we can show that this must be a negative length cycle. I'm going to skip the details because I now focus on the other case. All right. So what also can happen is the following. We start with this construction. Vertex U, we follow the path of predecessors, and that actually ends at start vertex S. Now I claim the following. If this is the case, then the vertex V is actually part of that path of predecessors. So remember that this path that we just constructed is the path P of U of predecessors of vertex U. And I'm actually claiming that somewhere on this path, we will find vertex V. Well, let's assume this is not the case. So let's assume V is not here. What can I say then? Well, then look at, Then look at this path here. So including the edge from U to V. So now this whole thing is a simple path of at most n-1 edges. But in the algorithm, we have done n-1 phases of this algorithm. So after n-1 phases, all the distance labels of this path of length at most n-1 must be correct. But our assumption up there is that the distance label along this final arc here is actually violated. So that's a contradiction. So indeed, this vertex V appears here in this path, and let's say it's here. Now let me complete the picture, because actually there exists this arc from U to V, which is the arc along which the triangle inequality is actually violated. And let me denote this subpath here as P prime. So that is this subpath from V to U. Now let us see what this gives us. What can I say about the distance label of U? Well, the distance label of U is equal to the distance label of V plus the length of the subpath P prime, right? Because the distance label of this guy, these are all tight edges, is equal to the distance label of V plus the length of the corresponding path. Now we know that the distance label of V, because this triangle inequality was violated, is larger than that of U plus the length of the arc. So we plug that in here. So this is larger than d of U plus the length of the arc from U to V plus the length of the path P prime, the subpath P prime. Now we can just cancel equal terms, and we observe that 0 is larger than the length of the arc from U to V plus the length of the path P prime, and that's it. And because this is in total obviously a negative length, but this is exactly the length of this cycle here. So we again have found a negative length cycle. Okay, so that finishes the proof that if there exists a violated triangle inequality after n-1 phases, then we can actually reconstruct a negative length cycle. So at the end, let us briefly look at the computation time of the Bellman-Ford algorithm. And that is actually very simple. So the claim is that the computation time is of order n times m, so number of edges times number of vertices of the graph. And why is that simple? Well, because the algorithm is simple. We have n-1 phases, and in each of these phases, we go over all the edges of the graph. And for each edge, we just have to do an update step if necessary. So that is constant time. So that's n-1 times order m. Okay, so the computation time follows by the fact that we have n-1 phases, and each of these phases goes over all the edges of the graph. Maybe a little practical remark, because if it happens to be the case that after, say, 5 phases, we realize that all the distance labels are correct, then we already have the proof that these distance labels represent the true shortest path lengths. And that means we can prematurely stop the algorithm, and we do not need to do all the other phases of the algorithm. In the worst case, this doesn't help, because there might be instances where we actually need all these n-1 phases. But for practical implementations, that helps a lot, because usually we are done after a couple of phases already. Okay, so that finishes the analysis of the Bellman-Ford algorithm. What have we done? We have computed shortest path lengths for graphs which are allowed to have negative length arcs and even negative length cycles. And in that case, we can also detect and compute these cycles. The next algorithm is going to be for a special case, namely when all the arc lengths are non-negative. And in that case, we can shave off this computation time, essentially an additional factor n. And that is known as the famous algorithm of Dijkstra. So computing shortest paths in directed graphs with non-negative arc lengths. Indeed, Dijkstra's algorithm is maybe one of the most famous algorithms of all in combinatorial optimization. And to some extent, most of you should have seen that algorithm before. But nevertheless, it cannot miss in a basic or introductory lecture on discrete optimization. So what's the idea? All the arc lengths or edge lengths are now non-negative. And the first insight is that when you think of the Bellman-Ford algorithm, it actually relaxes all the edges in each iteration. And that also has as a consequence that along some of the edges, we are actually making a correction step along the one and the same edge, maybe several times. So let me explain what I mean. So the claim here is that the Bellman-Ford algorithm relaxes one and the same arc possibly several times. And here by relax, I actually mean also needs to do an update step. Okay, let's look at this little example here. Small graph with 4 vertices. And let's assume the ordering of the edges is just given as first this edge, then this edge, then this edge, and then this edge. Okay, so that's the ordering of the edges. Now the initialization phase, of course, is the start vertex gets distance label 0 and all the other vertices get distance label plus infinity. So we do the first phase of the Bellman-Ford algorithm, and that means we are actually updating in the order of the edges. So this label gets updated to 5. Then we process the second edge. This label gets updated to 8. Then we process the edge from S to U, and this label gets updated to 2. And then we process the edge from U to V, and that actually means that this label gets updated to 3. So notice that we have processed or relaxed all the edges exactly once in this first phase, but nevertheless, as you already see here, there is another update step possible along the edge from V to W. So that is what we do in the second phase. So we go over all the edges once more. There is no update necessary along the first edge, but there is actually an update necessary once we process the edge from V to W for the second time. And indeed, so when doing that, 3 plus 3 is only 6. So we need another update of the distance label of W here. Then we continue processing this edge, nothing happens, and this edge, nothing happens, and we are actually done. But what you see here is that we actually needed these 2 update steps, at least given the ordering of the edges that I gave. We needed twice update steps for this edge. And that is something that can actually be avoided when the arc lengths are non-negative. And that's exactly the idea of Dijkstra's algorithm. I try to consider the edges in a very specific order. And by doing that in a more clever way, I can make sure that I need to correct each arc's triangle inequality only once. So each of the arcs or edges of the graph is processed or relaxed exactly once. And that saves computation time. And how do we organize this specific order of considering the edges of the graph? Well, we are considering the edges by actually processing vertices of the graph and considering edges as the edges outgoing of specific vertices. So let's see how Dijkstra actually does that. The initialization is just the same as before. Start vertex has distance 0, all the others plus infinity. Now we have this set V star. In the beginning, that's all vertices of the graph, and that contains the vertices that still have to be processed. And the complement of these that is going to be the vertices where the distance labels are already correct and represent the true shortest path lengths. Okay. So as long as there are still vertices to be processed, we continue. This is the most important step. We always pick the vertex among the vertices to be processed with the smallest distance label. So in the very first iteration, all vertices still need to be processed. So the only vertex that we can actually pick is the start vertex because it has label 0, while all the other vertices have label plus infinity. Okay. So we are processing the vertex u with smallest distance label. We are kicking that vertex u out of the vertices that still need to be processed. And the implicit assumption, and actually I'm going to prove that, is that the distance label of this vertex is already correct. Okay, so we are not going to process it anymore. And then we just do the following. For all the edges outgoing of that vertex u, we relax the corresponding edge. And notice by definition, this makes sure that all the edges of the graph are relaxed or processed exactly once only. So we stop when none of the vertices has to be processed anymore. So when all of the vertices have been processed. So let's look at a little example here. Graph with 5 vertices. In the beginning, we have to pick the vertex with the smallest distance label, which is the start vertex, which has label 0. We are processing the outgoing edges of that start vertex, which means we are going to update, if necessary, these distance labels. And that's what we do. So the distance label becomes 10 here and 5 here. Now we pick among all the vertices that still need to be processed, which is those here. We pick the one with smallest distance label, that is vertex with label 5 here. It has a couple of outgoing edges, and we're making the corresponding update step for those. So we see that this label gets updated to 5 plus 3. This label gets updated to 14, which is 9 plus 5. This label gets updated to 5 plus 2. Now again, we pick the one among all the vertices that still need to be processed, which is those. We pick the one with smallest distance label. It has outgoing edges, namely this one and this one. Now notice that these outgoing edges could also point backwards, so to say, towards the vertices that we already processed before. But as part of the correctness proof, you will see that along such an edge, never it's going to be the case that we need to update the distance label of these vertices here. And that is because the edge lengths are actually non-negative and by choice of the minimum distance label vertex. So we do the corresponding update here, which has the effect that the label of this vertex got updated. Let me look back. It was 14 before, and it is now 13. And as I said, nothing happens along this edge here. Okay. So once again, among these two guys, we pick the one with minimum label. I think the principle is clear. It has actually 2 outgoing arcs. And I see that there is going to be one more update possible here for the vertex with the label 13. And that's actually what we do. So this gets updated to 9 and nothing happens along this edge here. Now the final vertex is processed and there is no update happening anymore. We could as well skip that step. Okay, so we are done and we have computed shortest path lengths. Also notice that by definition of the algorithm, we have exactly looked at or considered each of the edges of the graph exactly once. So none of the edges has been considered twice or more. Okay, so let's see at the correctness proof. Why does this actually work? And the correctness proof is an inductive proof on the number of iterations of the algorithm, or if you wish, on the size of the set of vertices that have been processed already, which is, V without V star. Remember, V star is the set of vertices that still need to be processed. So this is the set of vertices that have been processed already. And it's an inductive proof on the size of this set. And the claim is for all these vertices that have been processed already, we have that the corresponding distance label is correct and is representing the true shortest path length. And because at the end of the algorithm, all vertices have been processed, this proves correctness of the algorithm, because at the end, all the vertices have been processed and nothing is left that still needs to be processed. So let us see how the correctness proof actually works. So I'm going to show that for the set of vertices that have been processed already, the distance labels are correct, are representing the true shortest path lengths by induction on the size of that set. The inductive start is simple because at the beginning, the only vertex that has the true distance label is the start vertex S. It has the label 0, which is actually correct. So our inductive start is done. And now let us consider some iteration of the algorithm where we have a set of vertices that have been processed already, of which I claim that these are having the true correct distance labels, and that's the inductive hypothesis here. And here on the right-hand side of the figure, you see a set of vertices of which the distance label is probably not yet correct, but we know that the distance label is actually larger or equal than the true shortest path distance. That must be true because they were initialized to plus infinity, and any update of a label actually corresponds to some existing path from the start vertex to that vertex V. So therefore, it corresponds to some SV path, and the shortest path could possibly only be shorter. Okay, so we know that all these distance labels might be larger than the true distance, but certainly not smaller. Now we look at an iteration where we process some vertex, and in this case, this vertex U up here. Okay, so this vertex U is the one which has the currently minimal label, distance label, among all the yet unprocessed vertices. What do I have to show? Well, I have to show that when I'm processing this vertex U, and actually that is already true before I'm processing it. So when I'm processing this vertex U, it is already having the shortest distance label. Okay, so the distance d of U is equal to delta of U. And well, what do I do when I process this vertex? Just to remind you, I'm considering all the outgoing edges for this vertex U, and I do the necessary updates, but the label of vertex U itself is not going to change in this iteration. Now, because this vertex had the minimum distance label among the unprocessed vertices, I know that this label must be finite. Okay, so we can consider some shortest path from S to U. Let's say this path has vertices V1 up to Vk. All right. Now, if all these vertices would have been processed already, that would correspond to the situation, for example, that the shortest SU path would be, for example, this one. Okay, so that would mean that all the predecessors of U had been processed already by the algorithm. So if that would be the case, because we already had processed the direct predecessor X of U, we would get the following observation. We would get that D of U is at most, that's a triangle inequality while processing this edge here, while relaxing this edge. D of U is not more than D of X plus the cost of the corresponding arc from X to U. But because X was already processed, this is actually equal to the true shortest path length. So delta of X plus the cost of the arc from X to U. And by assumption, this was actually the shortest path to get to vertex U, and therefore this would be equal to the true shortest path distance for U, but we just assumed that this is not the case, right? So we would have that D of U is smaller or equal than delta of U, but we assumed that it is actually strictly larger, so this cannot be. So therefore the situation must be different, and on this shortest path to visit vertex U, there must be some vertex on this path, some predecessor of U on this path, which belongs to the unprocessed vertices. So the actual situation rather looks, for example, like this, okay? And then this vertex y would be the predecessor of u that actually belongs to the unprocessed vertices. So among all these vertices, let us pick the one that is first on the path. So what I mean is let y be the first vertex on P, and here I mean in the order in which they appear on that path, and then in V star, so among the unprocessed vertices. So in our case, that is exactly this vertex y. Now this vertex y also has a predecessor, so let x be the predecessor of y on this path P. Now what can we observe here? Well, we see that d of y is at most d of x plus the length of the corresponding arc from x to y. Why is that? Well, that's because the corresponding arc has been relaxed already because x is on the left-hand side of the vertices that have been processed already. So we have been considering the outgoing arc of x, and we have been relaxing this arc if necessary. Now, by induction hypothesis, we know that, this distance label is correct because x has been processed already. So therefore, this is equal to delta of x plus the length of the corresponding arc. And now this amount here, delta of x plus the corresponding length of the arc, represents a subpath of the shortest path to get to vertex u. And because all the arc lengths are non-negative, this subpath, right, I mean that would be corresponding to this subpath, and because the arc length for this arc is certainly non-negative, we know that the subpath is cannot be longer than the true shortest path to get to vertex u. So this is at most delta of u. Well, and our assumption was that this is strictly smaller than the current label that vertex u has. So, but now look at what we got. So we have a vertex y here, which has not yet been processed. And we know that the distance label of that vertex y is actually strictly smaller than the distance label of vertex u. But Dijkstra's algorithm is defined in such a way that it always chooses the vertex with the smallest distance label. So therefore the choice of the algorithm would have been incorrect, and that is a contradiction. So that finishes the proof of the claim. And remember, the claim was by induction on the set or the size of the set of processed vertices that these vertices actually have the correct distance label. And because at the end of the algorithm, all vertices will have been processed, this is the correctness proof for Dijkstra's algorithm. Now let's briefly look at the computation time. And that is not too difficult. So as usual, we have to initialize the distance values. So we have to scan all the vertices of the graph. That takes order n time. And then we have actually n iterations of this while loop in which we always choose the minimum distance label vertex. And in each of these iterations, well, in order to choose the minimum label vertex, we have to find it. So the simplest thing that we can do is that we, if I go back to the proof, that we just scan all these vertices. So we just loop over all the vertices and always pick the one with a minimum label. That is what we can do. And in order to find this vertex u, that takes us order n time in the worst case, because we have to go over all the vertices on the right-hand side, right? So in total, since we are processing all the vertices, all the n vertices, that is n times order n, which in total gives us a computation time of order n squared. And how many updates are we actually doing? Well, in total, we are processing all the edges of the graph. Each of the edges is processed exactly once. So we are calling the relax function exactly m times, where m is the number of edges of the graph. So that's a computation time of order m. And now we just have to add up all of this. So that's order n plus order n squared plus order m. And everything is upper bounded by n squared, because the number of edges, as usual, cannot be more than order n squared. One can actually achieve a slightly better computation time, and that is when we use a more sophisticated data structure in order to compute in order to find the minimum label vertex. So notice that here, in order to find the vertex with the smallest distance label, we just scan all the vertices. If instead we use a priority queue, that is a data structure which always allows us to find the minimum label element in constant time, we can get an improvement in the total computation time and get it down to order m plus n log n. This log n here actually comes from the organization of the priority queue, because whenever we have to remove an element, we have to reshuffle this priority queue, and that gives us this log n overhead in the computation time here. All right, so we have seen two algorithms for computing shortest paths from S to all the other nodes. So that was Bellman, Forts, and Dijkstra's algorithm. And the computation times of these algorithms, in the worst case, were order n cubed in the worst case for dense graphs, for example, for Bellman-Fort, and order n squared for Dijkstra's algorithm for non-negative arc lengths, where this could be even improved to order m plus n log n, which is already very fast for practical purposes. There is yet another algorithm, namely when we have a cyclic graphs, so graphs that do not have any directed cycle, then we can get a computation time actually using a different and very simple dynamic programming algorithm of order n plus m, which is linear in the size of the graph. But that is not going to be treated in this lecture. Instead, I would like to focus in the remaining couple of minutes on the Floyd and Warshall algorithm, and that's an algorithm that actually computes all pairs of shortest paths between any two vertices u and v. Okay. So given is a directed graph and a cost function, as usual, arbitrary costs, and we want to determine shortest uv paths for all pairs of vertices u and v. And let's assume for simplicity that the graph G doesn't contain negative cost cycles, because we could detect or verify that using Bellman and Fort's algorithm upfront, for example. Now we define the same distance function. Delta is going to be the shortest path distances from between any pair of vertices u and v. Okay, so that's the infimum of all the paths, if they exist, between u and v, directed paths. And as before, we again concentrate only on the computation of these distance values, delta, because once we have those, we can very easily compute the shortest paths themselves. All right, the idea of Floyd and Warshall's algorithm is the following. That's the idea of so-called interior nodes. So what are interior nodes? Let's assume the vertices are labeled 1 up to n without loss of generality, and let P be a simple path from u to v. Okay, so v1 is the start vertex u, vl is the terminal vertex v, and then we say v2 up to vl minus 1 are the interior nodes of that path. Okay, and we are going to throw in a restriction on the interior nodes as follows. We call an uv path p an UVK path if it only uses interior nodes from the subset 1 up to k. Okay, when you look at this figure down here, we have vertex U here, we have vertex V there, and there is a path from U to V which only uses as interior nodes vertices from the subset 1 up to k and doesn't use any of the nodes k plus 1 up to n as interior nodes. There might be other paths from U to V, like this red one here, but that's not an UVK path. Okay, so UVK path means a path from U to V with interior nodes restricted to the subset of nodes 1 up to k. And I define the distance, the shortest possible distance, also with that restriction, and I call that delta k from U to V. So that's the infimum among all the paths from U to V, restricted to intermediate nodes 1 up to k. Now, what's the idea? The idea of Floyd's and Warshall's algorithm is to first compute delta 0, then compute delta 1 for all pairs of nodes, then compute delta 2, etc., up to computing delta n. What would delta n be? Well, delta n means shortest paths from U to V, where the interior nodes are restricted to being the nodes 1 up to n. So that's all the nodes, so there's no restriction at all. So as a matter of fact, delta n is just the same as delta, and that's what we want to compute. Another side remark, what for example would be delta 0? Delta 0 means paths from U to V with a restriction that there are no interior nodes. Okay, so that just means that delta 0 from U to V is just equal to the length of the corresponding arc, if it exists, and infinity otherwise. All right, so that is the goal. We want to compute shortest path distances between any pair of any pair of vertices U and V. That is delta UV for all U and V, and that is equal to delta n, and that is what we compute. So first compute delta 0. On the basis of delta 0, we can actually compute delta 1, then delta 2, and so on and so on. And then at the end we are done, having computed the true shortest path lengths between any pair of vertices. Now, how can we compute delta k from delta k minus 1 for arbitrary value k? Let's see how that works. Suppose we know, and we have already computed all these delta k minus 1 values. So that is shortest path distances with the restriction that interior nodes are only allowed from the subset 1 up to k minus 1. Okay. So let us consider an arbitrary shortest path from U to V restricted to the subset of nodes 1 up to k. Now, there is two cases that can show up. Either k is not an interior point of this path, which means that the shortest path, when I allow interior nodes 1 up to k, simply doesn't need node k, and therefore delta k would just be equal to delta k minus 1. So in picture, that just means that the shortest path from U to V, so this path P here, with intermediate nodes 1 up to k minus 1, is already shorter than any potential shortcut that this additional node k might offer. Okay, so all these paths here, which use k as intermediate nodes, are actually longer. Okay, so that means that interior node k is not necessary to get from U to V. And the other case is k is actually such an interior node. And in that case, we can just break up the path into two subpaths, right? So we have the subpath P1, which is a shortest path from U up to k. And we have subpath P2, which is a shortest path from k up to V. And notice that the intermediate nodes for these subpaths, so getting from U to k, will have restriction that interior nodes are only allowed from 1 up to k minus 1. and the same here. And in that case, we can compute the distance to get from U to V under the restriction that only interior nodes 1 up to K are allowed by splitting that up into a subpath to get to K and the subpath to get from K to V. So in a picture that would look as follows, we would have the subpath to get from U to K, right, using only intermediate nodes 1 up to K minus 1. And we have the subpath to get from K to V using only interior nodes 1 up to K minus 1 again. So these two cases are actually exclusive, and that means we have a very simple update step. So we can compute the value delta K by just looking up which of these two options is shorter, either allowing K or either taking K as an intermediate node or interior node of the shortest path between U and V, or not allowing that. And we take the shortest of these two options. That is a so-called dynamic programming algorithm because we have a parameter, in this case K, and computing the values for parameter K is just done by looking up the parameter values for parameter K minus 1, so 1 less. So we can think of that as follows. We build a whole table, 0, 1, etc., up to K, up to N. And we are computing delta K values in this table here. So such a column would correspond to the corresponding delta K value. And we can compute this value delta K here in this table by just looking up the corresponding values in the previous column, K minus 1, according to the update step that I just explained. So that's already the whole algorithm. So the pseudocode goes as follows. We initialize the distance between U and V to be 0 if U is equal to V. We set it equal to the length of the corresponding arc between U and V if that arc exists. And we set it to infinity otherwise. So that would be actually corresponding to the values delta 0 U V. So that's the first iteration, if you wish. And then we just see iteratively if allowing additional interior nodes improves the corresponding shortest paths or not. Okay, so we do that as follows. We iterate over this for loop. We iterate over this for loop here, going from 1 up to n. So this index k just means that in the kth iteration, we are computing values delta k. And in each such round or in each such loop, we go over all pairs of vertices of the graph. And we just check if allowing k as an intermediate node would give an improvement or not. So I look at the current distance between U and V. That was the distance delta k minus 1 actually. I compare it to the shortest distance if I allow k as an intermediate node. If this gives an improvement, then I do the corresponding update, and otherwise I leave this d unchanged, because otherwise that just means that k is not needed as an interior node on the shortest path from U to V. And that's all. And if you think about the computation time of this algorithm, that's also particularly simple. We just have this for loop that is n iterations, and in each iteration I look at all pairs of vertices, so that's order n squared, and I just have to make this check which takes constant time. So the computation time is of the order n times n squared, which gives me a computation time of order n to the 3 to compute all pairs of shortest paths with in the graph. Okay. Notice that this computation time looks large, but it's also computing a large output, right? So we are computing order n squared values because there is n squared shortest path distances between all these pairs of vertices. So given that this is a large output that we compute, order n to the cubed as a total computation time is actually not so bad. And it's also an algorithm which is particularly simple to implement. It's just a 3-line code in any programming language. All right, so this finishes the second lecture on shortest path algorithms. And let me announce that the last lecture is going to be about maximum flows, another classic in discrete optimization. And as you will see, for computing maximum flows, we already have the situation that we use or have to use shortest path computations as a subroutine for getting fast algorithms. So I thank you for your attention and see you for lecture number 3.